Good morning, everyone, and welcome once again to the JKMRC Friday Seminar series. On behalf of the University of Queensland and the Sustainable Minerals Institute, we'd like to acknowledge the traditional owners and custodians on the land on which we meet today. We pay our respect to the ancestors and their descendants who continue cultural and spiritual connections with country and recognize their valuable contribution to Australia and the global society. It's my great pleasure to welcome Dr. Jacek Kolacz. Jacek obtained his MSc degree in 1989 at the Mining University in Krakow in Poland. In 1985, he received the PhD degree at the Norwegian Institute of Technology in Norway. From 1984 to 2003, he worked at SINTEF Research Organization in Norway as a senior scientist. And then in 2003, he founded Comex Group companies in Norway and Poland, where he's currently working as a president. Comex provides sophisticated equipment and technological solutions in mining industry and material technology area. He is the author of over 150 papers published worldwide, international patents, and many scientific reports, mainly on sensor-based sorting. We're quite lucky today to have Jacek talk to us about our great scale-up of sensor-based sorting systems from test work to industrial applications. Please join me in welcoming Jacek.
Thank you very much. Okay. Can you hear me? Yeah, I hope so. Okay, I'm very glad that I can first of all come back to this area after many years. Actually, I have been here in the end of 90s, and so it's after 20 years, a lot of things changed, but it's nice to come back to the old buildings. And of course, I'm glad that we can talk about sorting. So sensor-based sorting, it's been a new thing in the industry, and it is slowly moving into the mining area. And we are really glad that this can bring a lot of benefits. So today, just a short introduction about Comex. So as already mentioned, we have been established in 2003 as a startup from SINTEF and NTNU University in Norway. And in 2007, we established a subsidiary company where we have currently a research center and the main production site. So if you want to see any equipment or all sensors installed, you have to visit this place here in Poland right now. We have a couple of satellite laboratories using different equipment, different sensors worldwide in different continents, but it is always, we always want to, our potential new customers, we want to see them in the main test center where we have possibility to test all possible sensors, and they are usually the newest types. Just the main groups, what we are working very shortly, we work with the powder technology. We started with the powder technology equipment, fine grinding, fine classification, comminution, basically. Different materials and different sizes down to a couple of microns top size. And sorting became more popular in, let's say, 2010. And currently it is the booming technology, I would say. We also have a particle characterization, industrial scale, based on Malvern. We built online particle size distribution equipment for different industrial applications, mainly online sensing. And also we use cameras for doing the same thing for coarser particles. Okay, and very quickly, just right now until today, we have over 500 installations worldwide in 27 countries, which are processing about 20 million tons annually. A lot of nice customers, and we are basically in all continents right now, so except Antarctic, you never know. Sensor-based sorting. So what is the difference between the equipment we provide and other known equipment? Is that the principle is the same. We provide the material as a monolayer on the vibrating feeder, and there we apply different sensors. And in our case, we use different technologies in the same unit. So that makes us different from other units that we can combine as a modular construction. We can combine different sensors and different technologies in the same machine. And if necessary, we can replace them or exchange them. Of course, the principle is the same, that you are analyzing the material, you make a decision which material is good or bad, and then you use the air ejection system to eject it to the separate line. We also have another sorting unit, which is with a 3-fraction unit, we call it, where we have 2 nozzles from the top and from the bottom, and then we can generate 3 fractions. So it could be a product, waste, and middlings, for example. So it's been started this year, basically. And what is the most important is that we use different sensors. So we almost always use XRT as a basic sensor. And then we use different technologies like XRF, RGB, regular cameras, or all types of infrared equipment, hyperspectral imaging and near infrared, 3D measurement of the thickness, laser dispersion, light dispersion, and gamma sensors for finding radioactive stuff, for example. And all this can be built in the same machine. So we create a kind of sandwich of information, and on the basis of this information, we make a decision. Is it bad or good material? Where we apply it, basically, normally we have a situation like this, that where there's a run-of-mine material, it goes directly to the processing plant, which creates a product like metal concentrate or whatever, and we generate a lot of waste. So we put our machine in between, sometimes at the mine, if possible, sometimes on the ground, if possible, and it can be also at the input of the processing plant. It depends on the situation and other conditions. But the main task is to generate the waste and to remove the same or similar waste concentration with a similar metal concentration and remove it in the early stage where the particles are large. So you can have a byproduct. You can sell this product instead of pay for landfilling. So we basically benefit that we remove the impurities in the early stage. We can the impurities are large, so they can be used for example, constructions, road building. We reduce the transportation to the plant, especially when the distance is significant. We lower the processing cost because we reduce the tonnage, producing the same amount of concentrate. And of course, we reduce the waste and disposal and increase product quality. So very often, all these advantages are taking place simultaneously. So at the end, we reduce the energy, we have a reduced cost and water consumption and the CO2 footprint. So it's beneficial. There is only one but, that the concentration of metal in this waste cannot be high. So you cannot lose too much material compared to the original situation. So what we normally, as a rule of thumb, we apply the conditions that the concentration in the waste stream here should be similar to the concentration of the metal in the waste traditionally today. Then nobody minds. And where we put it in the process, it's usually a multiple stage crushing, which ends in the milling and flotation, and we do the metallurgical stuff, and then of course we generate different types of wastes. So we put it in between, where we have sometimes between the crushing stages, sometimes between the crushing process and milling. So it depends on the conditions. It's not shown here that we need also screening. We need to have sizes not smaller than 10 millimeters, because it's not economic to have sorting of small particles. For high value materials, yes, we have sorters even from 2 to 6 millimeters, but this is very high quality material. For regular ores, it is not really profitable. Even we go more than that, it's 15 or 20 millimeters as a bottom size. And then the upper size, approximately 100, 150. Depends on the technology we use. Scale up from the laboratory scale. That's a very important thing, because the one thing is to establish the conditions for sorting, but the second thing is to improve it or optimize it. So to do it, we provide, for a couple of years, we started to provide different types of laboratory scanners or laboratory sorting machines, which are, first, they were very, I would say, simple solutions with single sensors. But the last type, which we have already now for about a year on the market, It contains every sensor we have in our portfolio, so we can have a possibility to do research work separately. And then we can introduce it to the large machines like these, where we have a capacity difference between, let's say, a couple of rocks per minute, up to maybe, I would say, 50 kilograms per hour, 100 kilograms per hour. And here we have a couple of tons to a couple of 100 tons per hour. So it depends on which size. This is 1 meter machine, 2 meter machines, and we build also parallel lines of 2 meter machines. So this can go at the end about up to even 1,000 tons per hour. So it's depends for large particles. So the main thing is that when you have industrial machine, nobody allows you to do a lot of research. I mean, to destroy the product. So when we have this machine, we can do everything possible. And then, of course, when we are ready with the final conclusions, we can transfer the what we call sorting file to the machine which is operating, and then very quickly optimize it. So it helps a lot to follow the right way of doing it. Of course, the assumption is that it has to be our equipment, so it doesn't work for the competition. What we have in this laboratory unit, we have all the sensors we use. We have RGB cameras, regular lights, I mean the visible light. We have XRF sensors, we have X-ray transmission, we have a laser sensor for geometry and thickness, and we have hyperspectral imaging as well. So we can move the particles back and forth, and then at the end, we decide which one is working as a most promising one. And then these can be used as a sorting mode. And then at the end of the belt, we have mechanical flaps, so they can simulate the real operation of the sorting machine. So at the end of a test, you have two fractions, like you will have them in the industrial scale. So it helps also to convince the mining engineers that you can produce two fractions. So it's not on the paper. It's not mixed on the paper. Okay, so you can physically have two fractions, and you can make chemical assays and provide the nice report, which is much more convincing. This is how the machine looks like, but the best is to see it on this short movie. So it's very compact machine with different sensors, as I already mentioned. It goes a little bit through some introduction, but has a separate PC, so you can operate it from the machine, or you can operate it remotely. But the most important, it has all these sensors, which I already mentioned, in the same unit. So we normally put the material inside a drawer or on the belt. We have also an option to feed it by vibrating feeder, so you can make it continuous if you want. And then the material goes through different parts of the sensors. So as I mentioned, XRT is the basic one. Then it's a RGB camera. We have XRF, laser, and 3D cam. And at the end, we go through the hyperspectral imaging, which requires a lot of lighting, and the gamma sensor. So in the sorting mode, this works like that. That's just separate the rocks separately to the different boxes, and that's what we think it's a very valuable part of the machine, that you can change parameters, you can change characteristics of analysis, and the machine can still produce the two fractions at the end. Okay, sorting technology, we normally operate in the electromagnetic radiation area with different frequencies. So normally we have a visible light. It's it's a tradition in sorting for many years to use a visible light area, but this is of course only a short section of possibilities. We have an infrared possibility, which is a very exciting area, especially shortwave infrared, where the minerals can be visible in a different way. We have X-rays and gamma rays, but the best is the combination of X-rays and these here, I mean the visible and infrared. So regarding the XRT first, it's a traditional one. It's, I think, known for everybody. It's, if anyone travels, goes through the airport machine, it's the same technology. They do the similar work. They try to find organic stuff, explosives, or different metals, objects. We do the same, but we are looking for metal concentrations of different grades, and we do it a bit faster and more accurately. The technology is the same. At the end, we have a X-ray image, which we process differently. I will come back to this. But these images will depend on different phenomena which are taking place in material sensing. So this is a nice animation just showing that some X-rays are passing the material without any collision. So we have to measure it and we have to register it. So we have it as a background. We have also a photoelectric effect where the X-ray energy rejects electrons from the first orbit. Then we have a fall of the electrons from the next one, and then we generate a certain amount of X-ray, which is characteristics for the matter. This happens also from the first or from the second orbit, and then we have a different primary and secondary information. We have also Compton scattering, which disturbs us a little bit, because the photons, X-ray photons, change the direction and energy. There's also Rayleigh effect, which is even stronger, that it changes the direction without changing energy. So all this is necessary to process together and make at the end a decision. Is it good for one material? Is it bad for the other one? And then try to compensate it with a certain configuration of the X-ray detector. So the effect is very nice because normally we don't see anything. This is an example of an iron ore. When we have an X-ray image, we can see the very nice inclusions of the material. We see the very high, I mean, blue is low density, red and yellow is a high density material. Here, very nicely concentrated iron ore. Here it's complete waste, which can be removed without any metal losses. Here it's a little combination. We decide, it's up to us to adjust. Shall we treat this one, both of them as a waste, or shall we have it as a middle fraction, or whatever we want? So there is a possibility to make grading of every single rock. The analysis is the traditional one. We have a spectra of different energy X-ray attenuation in different energy levels. So different materials, they attenuate X-ray differently. And that's the point, how we can choose different energy levels to see the best difference. And we adjust this energy level to get the difference as significant as possible. The effect is like this. We calculate on the basis of this analysis, we calculate pixels of the material which we think is valuable in this case. This is an example of zinc and lead ore. So again, everything which is blue is a regular rock, like 2.5, 2.6 specific gravity. And everything which is yellow is higher, the green is the highest. So we can actually calculate number of pixels, we can calculate number of spots. We can also calculate how the pattern appears in each of the rocks. So not only the number of pixels and against the background, but also how the pixels are distributed on the complete image of the particle. So all this must be done more or less in approximately 5 milliseconds. And then you have to make a decision that, okay, it's a bad rock, it's a good rock. So it's a pretty fast system. There is one more technology which we tried to introduce, but it's not easy to apply. It's because the pixels I showed you before was, you can go to 0.8 millimeter resolution. But if you want to go to the finer resolution, if you want to see some very small inclusions, then we have to go to the high definition detectors, which are built in a bit different way. There is an array of small lines, analyzing lines up to 128 pixel lines. And we do the imaging simultaneously. The reason is following. When we do the regular object analysis with the line scanning, then we are building an image line by line. So we are scanning one line, the second line, third one, and so on. But if you can imagine, if you go from 0.8 to 0.1 resolution, like in this case, then the number of photons falling into the detector is decreasing dramatically. So your image will be very weak. So basically, at the end, you will have a very, I would say, unclear image of the particles. So no special benefit. So that's why we use the TDA, which is a time differentiated integration. So it works that way, that we are analyzing a number of lines, like 128 at the same time. But then we only build the first line, and then when the particle moves, then we are building and adding the next image on top of the previous one. So in that way, we are constructing a new image directly based on the 128 layers. And we add them together. So at the end, we have a very nice, clear image of the particle with a very high resolution. But of course, you can imagine this process is not so fast. Despite very highly efficient electronics today, we are still not able to gain higher belt speed than 1.5 meters per second, while we have in the traditional way, we have 3 meters per second speed of the belt. So it's a limitation. It immediately reduces the capacity. And of course, you can also imagine that if you increase the line resolution by 10 times, for example, then it means 100 times more data to process during the same time unit. So it's a huge amount of information to filter after that and make a decision if it's bad or good particle. It's still too complicated. We are waiting until this electronic system will become maybe more efficient, and then it can be introduced to mining. The effect is, of course, nice. Here's the example of the image done with a traditional sensor with a 0.8 resolution. And here we have just a fraction of this rock with this high resolution image. And that is very nice. So we see the blue ones with a regular rock. The yellow is, I think in this case, it was an iron ore. And the red one is the contamination of the ore, which is cinnabarite. It's a mercury contamination. So we can detect the number of the concentration of mercury and remove the particle if necessary. So it can work very nicely for some applications. We have the sensor in our analyzer, but we don't have it yet introduced in the real sorting unit in the industry. Another example how we can see the very nice spots, very small inclusions based on the attenuation characteristics. So, for example, we can see gold particles of 0.1 millimeter size. But unfortunately, gold is much finer, so it doesn't help always. RGB imaging is very simple. Fortunately, this is the best sensor, so it's been on the market for many years, and this technology has been developed a long time ago. Now we have a very nice cameras available, very nice and fixed characteristics with 3 planes, red, green, and blue. We have a resolution of the best resolution, 0.1, 0.2, without any problems, without any limitations. And we have a scanning rates up to even 20 kilohertz with colors, so 40 kilohertz monochromatic. So every 50 microseconds approximately, it's more than enough for us to do the imaging. We don't need it. We don't even need it. What is the result from the optical cameras that we can build different areas of, we can mark the areas on the particles depending on the color combination or color appearance, and make parameters out of it. So based on these parameters, we can apply thresholds to qualify this particle as acceptable or not, or a kind of additional feature for combining this into the image, as I showed at the beginning when we build the sandwich of the information. Then it could be an additional parameter to make a decision into the X-ray, for example, analysis as a extra information. Shortwave infrared hyperspectral imaging. It's very interesting because we can see here is the reflectance depending on the wavelength of the light. If we look at the visible light range, we see that not very much is happening. For example, when we take calcite and the feldspar, then we see there is similar characteristics in visible light. That means you don't see difference, and that's correct because both of them are white. Then we look at the near infrared, it's basically the same. But when you go to the shortwave infrared area, then the variations are huge. So we can utilize this part between 2 and 2.4 microns or 2000 nanometers and 2004 to find differences. And that helps a lot. This is, for example, as different spectra from different copper ores with a sandstone based and carbonate based ore. So we can differentiate these spectra, and we can actually separate them. So the benefit can be that you don't produce waste in this kind of sorting, but you produce material 1 and material 2, and you can process them separately in the separate flotation lines. So make it much more efficient, because it's really complicated to have flotation process which fits for all material, all types of material. From the SWIR analysis, we see we have also possibility to have a very nice mineralogical image of the surface. Of course, this is a low speed scanning. It's like we send it through the scanner in the research stage during the research stage. So we can differentiate different parts of minerals. We have also even a connection to the database from the USGS, so we can get some help regarding different spectra. But in most of the cases, our experience says that it has to be done separately. You have to do it manually, because every ore is different, every rock is different, even every deposit is different. So you have to build your own database, basically. But it can be a kind of good indication where to look for. When we use the high speed, and when we apply this SWIR analysis in high speed during sorting, then the images are much worse. But this is basically the working image of the rocks moving with a high speed. So that means we are just looking for some single pixel information. That in this case, the red color is the regular rock or the rest of the rock, and the blue one is the material we are interested in. So we are just calculating the ratio very quickly, what is blue against red, and make a decision, is it to be rejected or not. So it's a different approach. We don't have much time for that. So as I said, we have a couple of milliseconds to do every stage of analysis. So maybe altogether will be 20 milliseconds. It's still very short. We also have a possibility to investigate the lithology of the material. Here is the example of 3 different copper types, where we have from the lab. This is the expected lithology which we have from the customer, and then we try to simulate the same or reproduce the same in our sorter. So sometimes it's a very good fit. Sometimes the fit is varying during the operation, but still the tendency is clear that in some cases it repeats properly. And for the third fraction, it's the same. So sometimes the first sample is different, the second one is good, but basically the tendency is easy to recognize. So this tendency can be still used for finding a proper decision. And the good thing is that when you are separating carbonates from sandstone material, then you don't have waste. So you basically create 2 separate flotation lines. So you are just improving the flotation. You are not losing anything. So it works. At the end of the day, it works better than when you mix it all together and try to have a general flotation for everything. XRF analysis, we provide very high speed, very special high speed sensors. These sensors, by the way, are the same ones which are sent to Mars in this European spaceship. So exactly the same unit. We use many of them collimated, so we can see the whole width of the belt. And the response is a bit special. Here we have the same samples which I showed between the carbonates and sandstone. And these samples are here. And basically we have the response in the form of the different peaks and different signals. But the correlation is very good, because here are the chemical assays, and they correlate very nicely with the height of the signal. So we have, of course, we use mostly primary frequency, but we can also use secondary in case there is a mass with the other material. So we don't have a good recognition because it's very complex analysis. So at the end, we just build a model that we are interested in one channel. We have a one threshold, and if this threshold exceeds the signal exceeds the threshold, then it is treated as a good material or material which has a value. So we don't need to reject it. So X-ray analysis says that, okay, it's maybe waste, but if the XRF says, no, there's a copper inside, then we still keep it, don't reject it. So it's a good combination. And offline combination and data fusion is of course very critical. Here's again the example of the X-ray analysis, XRT, which the signal goes to the computing unit. Then we have hyperspectral imaging going to the same unit. And then we have a collimated XRF, which can go to the same unit. So at the end, we can build a model which can, by different types of calculations and compromises, it can, in a very short time, give you the message that, okay, it is either good pixel or good particle, because we can do it both on the pixel level and the particle level. Resolution correction is, of course, very crucial because all these sensors have completely different working principle, different speeds, so they provide different resolution. Here the X-ray sensor is from 0.1, which I still keep it as a reserve. It's mostly 0.8 millimeters standard resolution. And then we have a RGB sensor with a 0.1, very nice. We have a SWIR hyperspectral. Usually it is 2 to 3 millimeters resolution because it's really expensive equipment and you can't put many cameras over the belt, so you have to really optimize it. So we have a very big difference between the different types of equipment. And of course, XRF is 25 millimeter resolution because it's 1 inch basically squares we are looking at. So just we are just asking for information if there is any certain metal inside or element. And then the gamma sensor is the same, even higher. So it is also just to say that this is a radioactive material, remove it. Very often the radioactive material is removed by very seldom. I mean, it's maybe 1% concentration or 0.5% concentration, and people want to have this as a just to purify the material from radioactive stuff. So that means it's more than enough. So in case we remove some other material, by the way, it's not a problem because we can always do the secondary scanning and then separate it very precisely. All these sensors can be built in a kind of matrix. So here's the example that you can, for example, you can use AVC, I mean the XRT, RGB, and SWIR analysis in the same unit, in the same at the same time. And then you can build your own logics. For example, you have different thresholds for each of the analysis, and you can provide, for example, low, high, or high and low. You can leave it empty. You have a full flexibility how to organize the metrics of separation for identifying the right material. So it's a very powerful tool for when you have all these sensors available together. And at the end, we have a deep learning option for finding simple differences between concrete elements, I mean concrete particles. So this is a separator model. We have particles of different structures. For example, like X-ray particles. X-ray analysis gives us two particle types. So we try to teach the model with, for example, 400 samples, that this is the product, 400 samples, this is the waste, and see how the model responds on this result. Usually it is very sensitive for not making enough samples, and also it's very sensitive for over-tuning. So if you put too many samples, then the model treats everything equally. So basically, and you can imagine the number of combinations because this is a deep learning process which goes automatically. You program it and you have it a couple of hours, maybe it's done. But then when you change the parameter of one of the sensors a little bit differently, then it's a different pixel resolution. Then you have to do the same again. So it's a endless process. So this is really a new thing now introduced in sorting. So it helps a lot for segmentation, for example, for finding when the particles are lying on top of each other or close to each other. So we can separate them on the belt. So this model can help a lot. But for sorting and structure analysis, it's very complex. We are just starting it. We call this model cats and dogs. So it's when you make 400 images of cats and 400 images of dogs, you should be able to recognize every cat and every dog. So it depends in which continent maybe, but just in case. Okay, what is the result from the combination of different sensors? A practical result. This is an example of the rare earth sorting, where we have a combination of XRT and hyperspectral imaging. This is the product part. This is the waste part. Different groups. You see images are showing clearly that this is a lot of green and the yellow color. Here, this is much less. But this hyperspectral imaging is giving us additional information saying that, okay, this is low value material or high value material. So combining it gives us a very nice result in form of from A to D is the product, and from E to H is a low content of total rare earth and oxides. So in both cases, it works pretty well. This is, by the way, our patented solution. So it's a COMEX technology regarding this combination of these two sensors, because it's crucial for sorting of some minerals, especially rare earths, where you have a mineralogical and atomic density analysis in the same time. And the application examples, what we did based on this scale up, which I mentioned, which is very critical from the small to the large unit. We applied it, for example, in some lead and zinc ore in this case, with a low grade, 1.8 of zinc and 0.8 of lead, increasing to the product, having it almost 11 to 5, so it's a quite high difference. And not losing too much. If you look at the recovery, it's 87 and about 80% recovery. But you are eliminating 87% of waste. So your processing plant is receiving only 13% of the initial input. So it's a huge difference. And this was actually approved after that in the industrial scale. The same thing was done with a bit richer ore, where we had initially 6.8 of zinc and 22 very rich lead. This was increased to almost to the concentrate, but we had possibility to produce also middlings and real waste, which is containing almost no metals. So depending what the customer wants, it's possible to make a great recovery curves and choose the right concentration. At the base of this was we built the sorting plant for this mine, where we started with, at the end of the day, we started with almost 8% of zinc and 4.7 of lead in average. And this was pre-concentrated to 14 and 8. And the recoveries were at the range of 90%. But split between by weight was 50-50. So that means very encouraging. So half of the processing plant capacity was occupied. It's a nicer image showing here the different options when we have the mass recovery of the product and waste, and here is the ore kept or recovery. So obviously we start with 100 recovery at the beginning, and then you see it's very flat and very nice curve until 50-50 split. So we are losing up to 8-7% of metal. Oh, sorry. But of course, eliminating 50% of the initial mass. So usually people want to work in this range. Of course, nobody wants to go down there because it's too high losses. Another interesting combination. We did a test with a small unit with XRT test with sorting copper and gold, or with separate sensors. First XRT, we started with 44%. It's of course not a gold grade, but it's the particles were marked with the particles which are interesting, which are treated as a good particle, good product for further processing, and the particles which were not having any metal, they were treated as a second type. So in this case, 44%, that means 44% of the rocks which are interesting for further processing. The rest is waste. So we made the first simulation, so we could do a lot of tests, repeat them many times with different sensors, different settings, and that is quite good approach to work with a limited batch, because then you can do a lot of calculations, you can do a lot of back calculations, and so on. And then we did the same with when we applied RGB, regular visible light analysis, in addition to the X-ray. And here we started with it was a bit different feed, but it doesn't matter. You see, we started with 44, was upgraded to 75, and the recovery was 94 approximately. We started with 53, much higher grade at the end, and 99.1 recovery. So recovery is a crucial thing. So in this case, we could eliminate almost 45%, 44% of waste, but not losing any metal. So that means it's absolutely different from more or less removing the same 45%, but losing 7% or 6% of the metal. So it's the combination definitely helps in this case. So on the basis of this result, we built a sorter with 2 sensors and applied it in the industrial scale. It's I will have a nice movie showing this application. And here we have a combination of sensors in the full scale operation. So we did a test with a large batch of 1,200 tons. And then we started with 1.2 grams per ton, because now we are talking, of course, about the real concentration of gold. 1.2. Which was pre-concentrated to 517, and in the waste we had 0.5. 0.5, the reason that it was 0.5 was that this is a cutoff grade for this plant. So if necessary to reduce to lower amount, we can do to 0.4, 0.3, usually not less than that. But 0.5 is a good number anyway. So the recovery of total gold is 65, approximately 65%. But if we reduce, of course, this number, then we increase the recovery. So it's a trade-off. But the good thing is here, you see 15% of the product, 85% of the waste. So that means they are keeping the same amount of metal production, but treating only 15% of the initial mass. So it's a huge benefit on everything. This is how the sensors are built in reality during production. This is our assembly plant. The example of the sorter with a regular camera is here. This is a sorter with a hyperspectral imaging. It's a bit more complicated because of the cooling and safety issues, because you can imagine that in the hyperspectral imaging, we use the halogen lights, and very high intensity halogen lights. And this intensity is so high that when you stop the belt is burning. So it's actually unfortunately necessary to provide a safety system that when the belt stops, light goes off. So that's very simple. Normally it's not a problem. We can also build it, like in this case, in the container. So this is a magnesite production plant. And if necessary for higher capacities, as I already mentioned, here we have an application in China, and we can build parallel lines. These are 2-meter units working in parallel lines. So depending on the particle size, you can go from a couple of hundred to even up to 1,000 tons per hour for this capacity. Of course, if necessary to have more, you can build as many lines as you like. The good thing is that the capex, the OpEx, the operating cost is still the same, approximately $0.1 per ton of the process material. It's really, really low. And the capex is changing, but of course the capex will have completely different calculation, because you are processing 1,000 tons per hour. It's a huge amount. So it's also within the same proportions. In any case, it's a profit for the user. And finally, I hope it's a nice movie from this application, which I already mentioned with gold and copper. This is a real plant applied about 5-6 years ago. Now we have a second line working already second year. And you see the vein of copper and gold, very narrow. So they have to mine everything. So everything before was ground and going through the CIP process and with all these necessary chemicals and so on. Now this is a brownfield application, so we built this plant in addition. Here we have the incoming material with 1.2 grams per ton concentration. It has to go through washing because of this optical sensor. If we don't use optical, we don't need to wash it. But in this case, it was necessary. It goes to the sorting plant. Here we have the sorter inside the container with protecting from wind and rain and humidity and so on with the air conditioning. So the material is provided on the vibrating feeder. It goes through the optical sensor and the X-ray, which you don't see. And then every particle is described with a separate assay, of course, relatively by the sensors. And here we see that the material has something interesting. So then what we do is we just reject it. In this case, we are rejecting product because it's much less of the product. So we are always rejecting the fraction, which is less, just to save on compressed air. And now the result, you see the belt is much less loaded, but it's a very nicely concentrated sulfides with a lot of interesting material. And here's the belt, a huge tonnage, but without anything interesting in it. So at the end, we have pre-concentrated material to 5 to 6 grams per ton. It's only 15% by weight compared to the initial input. And then the other one will be the waste, 0.3 to 0.5 and 85% by weight. So it's definitely below the cutoff grade. The result is pre-concentrating 5 times. Of course, the size fraction, so you have to mix it with a fine fraction, so it's a bit less, but it's 6 times less processing waste. So that's a huge difference. So just the conclusions. So the sensor combination, especially with the XRT and infrared, RGB or XRF gamma, it represents the important progress for efficient material detection, and especially for metal ores for mining applications. But they need to be optimized, and this can be done in the very nice by very precise work in the laboratory scale before you apply it in the industrial scale. And first of all, you have to find out which combination is best before you decide that you have to build this sorter with these sensors. Optimization must be individual for every detection, for every sensor type, different settings, different calculating models separately, and then before you put them together. Sensor configuration, both hardware, firmware development, dedicated electronic circuit solutions. It's a crucial thing because these things are, as I mentioned, we have just few milliseconds to make decision. And this is really not, it doesn't fit to the regular computer stuff. So we need a very special dedicated electronics to make a decision in a very short time. Data fusion, of course, it's a crucial thing for making this, combine these signals from different sensors, and the final configuration settings to optimize it as an overall process. So this LSX laboratory unit is a very helpful tool for us to start with, because the results can be scaled up directly. You can adjust the exposure. For example, when you are doing it with a certain speed at a certain scale in the industry, you can adjust the speed of the belt in the laboratory scale and the exposure time. So you can simulate the same conditions for high speed operation. So it doesn't need to be tested with a high speed in the laboratory scale. And of course, the optimal settings can be exported directly. So that's it. Thank you very much for your kind attention.
Any questions?
Thanks, that looks really cool. A quick question about the hyperspectral sensors, the shortwave infrared and thermal infrared that you have there. Samples need to be dry for that technique to work efficiently, but you said you have to wash the samples prior to sensing as well. Do you have like a drying stage in there, or how does that work?
Normally we have just dewatering. I mean, there is a washing stage and there is a washing screen without any water. So just shaking the water off, and then that's it. That's usually enough. You don't need to dry it. It's of course it depends on the characteristics of the rocks, of the surface. If they keep still the liquid phase too much, giving us a lot of reflections, so that is a little bit, it needs more time. Okay, but normally it is just enough to, it's helping to have it a bit wet, moist, so you don't need to dry it. It will be even negative. So but it helps, but it cannot be too much water, so the reflections are critical.
Thanks.
Thank you. That was really cool. One question for you, that there's sort of a direction that analysis, I suppose, is going, especially in, say, the lithium world, is LIBS. And there are people developing inline LIBS systems at the moment. What's your feeling about the combination of any of those parameters you've got with, say, putting LIBS in there?
We tested LIBS very, very long time ago in aluminum recycling projects, and it worked perfectly. But of course, in recycling, the case was very clear. Pieces of elements or particles were very homogeneous, or not very homogeneous, but they were at least they consisted of 2-3 material types. So when you were able to shoot maybe 10 times per particle, you could say, okay, this is more or less safe. It gives us a full image of the composition. But if you shoot 10 times on the mineral particle, you are still not sure. You shoot 100 times, you are still not sure. You do it 1,000 times, maybe. So the drill core analyzers, for example, they use a LIBS technique for analyzing. But for sorting, I don't think it's a good idea. I mean, we have this in our portfolio that we can use it as a safety switch. So if there is a application where we can really apply it, yes, we could do it. But first of all, equipment is very expensive. It's much more expensive than the shortwave infrared, which became affordable in the last years. Safety issues as well, because it's a high intensity laser. Reflections from some shining areas, you have to eliminate it completely. So it's and you just need, for your eyes to damage, you need just milliseconds of a high radiation of laser, and that's it. If you get the X-ray for the same time, and nothing happens. It's you get it like you make a picture at the dentist. So it's basically there are a lot of issues which I think are making this application as still negative for mineral industry, especially because the spot is 1 square millimeter basically.
It's like down at 51 comes out.
Exactly. So it's and what is inside, we don't know. We don't know what we are looking at, and the overall image is. I mean, the important thing is the overall image. So when we use XRF instead, then we radiate the whole surface quite equally with plenty of photons, and then we get a message from one place. Okay, there is a metal here. Then we can make a model. Okay, we have certain amount of feedback photons, and then we can calculate. That's my personal opinion. We don't go for it. It's not our core activity today.
Thank you, Jacek. First a clarification, then a question. With the XRT, you mentioned density. Just clarifying, you're talking about atomic density, not mineral SG.
Yeah, it's an atomic density. It's an atomic density group, basically. So it can be anything in this group. So basically, it correlates very well with the regular density. So it helps, but you get quite a complex image, and all these phenomena which I showed at the beginning are in a way making a mess in addition, because we have a combination of metals, a combination of different matter, And then we have, in addition, not really direct measurement of the density. So we build different models with different correlation models for different ores. And then on the base of this, we can calibrate equipment for regular density. So it can make sense. But once you go to the next deposit, you have to do the calibration again. So.
And then the question then leading on from that, have you had an opportunity to do a direct comparison with dense medium separation, for instance?
Yes, that's a very nice question, because the Zinc and Lead project, we replaced exactly the heavy media separation equipment with a sorting unit. And it was very interesting comparison. First of all, we were able to provide much lower losses because the analysis of the structure, how the high density material is positioned inside the rock, was possible to detect much better, because in the sink and float method, you have just the direct measurement. There's only one parameter. And in addition to this parameter, you have this effect of the mechanical collisions, that particles they are very heavy, very light, it's clear they are going to the right directions. But sometimes when they are close to the cut point, separating point, and when they are hit by accidental particles, then they end up in the wrong fraction very easily. Here, the sorting is a very digital. It's 0 or 1. It's full air pulse or no pulse. So the physical separation is very clear. The only thing is the analysis. The analysis must be done the right way. So it was much better cutting line for these particles, and a huge difference in operating costs. Because in this process, we don't have any media. I mean, no magnetite or ferrosilicon or whatever. So it's no pumping, no slurry control, and specific gravity control, and so on. So it's been, I don't remember the numbers, but as I mentioned, $0.1 per ton is our process cost, operating cost, and I think it was compared to about $3 to $5 as a cheapest option. And many plants are operating even higher. So it's a huge benefit compared to this. Of course, it doesn't work below 10 millimeters. So this fraction must be treated separately in a jig or in a heavy media separation if you make it.
You've emphasized that you must especially tune your system to specific ores. What about variability of ores coming from a mine? Maybe different areas of the mine varying over time. Can you really fall off the edge of your efficiency where it can misdetect or become ineffectual?
Yeah, absolutely. Good question. It's during our commissioning process, we try to send the clear message to the operators that it's not a magic box which works by itself. So it doesn't mean that it will adjust the parameters itself. So they have to really feel the machine, how it works for different deposits. So basically, we try to convince people that you have of course a lot of adjusting parameters during the sorting process. So you can go to just different slides, and you can see that, okay, if you reduce this one, then you purify the material at the output, but you are losing more material in the waste. And this is a trade-off which you, after using it for a couple of weeks, you find out the flexibility. So when the new deposit comes, then you usually know what to do. I mean, if it's a problem, we normally ask our customers to make scanning of this new material, even on their material, because we can remotely scan it, and then we can find out the parameters which could be better for this process, for the new process, if they ask for it. But basically, surprisingly, they can manage by themselves, and they do it pretty well. Because after using this machine and finding these adjustment parameters, you really you see the possibilities. The worst thing is that only when people don't touch it, so we don't like it. And of course, the remote connection helps a lot. We have the same option in the lab to do. So if they send us samples, just a couple of 100 rocks of new material, which they have no idea how to adjust it, then we can say, okay, for example, don't even try it because it doesn't fit for sorting at all, because it can happen. If it's a fully disseminated material, no sorting, but very seldom like that. different options.
So although it's 0 or 1, cats and dogs, so you're talking about assessing this, can you see as, you know, you've got this line where you have the cutoff, can you see as the material is getting closer and closer, or how the average material input is actually changing? Is that a constant part of the measurement? Because obviously you can't say cats and dogs will ever get close together, but you sort of see what I mean with the rock situation, that they may actually merge into something where that boundary is a bit softer.
Obviously, it is a big influence. So when there is when the rocks look very similar on X-ray images, basically by looking at them, you see that there is a very little difference between them. So that then this model might fail. But surprisingly, even when we see that there is a challenging case, when we teach the system, surprisingly, the result is that the model does something, and it's working. Of course, not working ideally, but it's not like when you have clear differences. But surprisingly, if you would be having many minutes to look at different printouts and do judgment by yourself, you would not make this separation at all. So the model really does something which is, I would say, not magic, but it looks at tiny differences which are not visible by, I mean, the human being is not able to analyze it statistically. So that's the main point. So that's why AI is a bit better, but not always better.
Okay, please join me in thanking Jacek once again.
Thank you.
Next week, we have Martin Lynch from SMI. He's going to talk to us about substitutes for copper, if there is any. Thanks.